Welcome back. We're going to go ahead and continue our discussion on the gradient and its impact in order to find the directional derivatives. So for question number 2, we are asked to find the directional derivative if we have the following function: e to the x minus 1 plus e to the y plus 2x. Now we're standing at the point on this function, we're standing at an x coordinate of 1 and a y coordinate of 0. But we want to move into this direction. So this is going to give me my direction. So I can find u pretty quickly. Now, to get u, remember this is our direction vector. And earlier we said the one way to find u is to get the cosine of theta and the sine of theta. That's a quick way to get a unit vector if I'm given an angle. So this is going to become the cosine of 7 pi over 6. Which we should remember from pre-cal is negative root 3 over 2. We're in the third quadrant. And the sine of 7 pi over 6, which is negative a half. Now, we already know that this is going to be a unit vector because we're using our cosine sine theta. I can easily guarantee this because my Pythagorean, cosine squared plus sine squared is 1. So this has to be a unit vector. So that's the first thing we're going to need. Because remember, to get our directional vector, we are going to take, our rule says, to take the del x1, dot that with u. Now remember, it is del, and that is the correct way to put it. But also remember, this is the gradient. We talked about the gradient earlier. Dot with u. So we're using that. This is an application of the gradient. So let's go ahead. First thing we have to find, of course, is our gradient, our del f. So del and the gradient, I kind of use them synonymously if you notice, but they are a little bit different. Del is more of a function. It's in terms of x and y. So the gradient is in terms of the values. Once you plug your point in, that gives you the gradient. So del is an operator, so we can use it for a lot of different things. So del f, if I take my derivative, we're going to get e to the x minus 1 plus 2, and let's see here, the derivative with respect to y is just going to become e to the y. So there is my del. To get my gradient, I'm now going to plug in the point. Well, we're standing at the point 1, 0. Plugging in the point 1, 0, we're going to get, what's that become? 0 e to the 0, which is 1, plus 2, which is 3, and e to the y, which is 0, is 1. So this is actually my gradient right here. And remember, what does the gradient tell us? Well, this is the direction of maximum increase on f. On f. So if you're standing on this function, this direction is going to give us the direction of maximum increase. I can find the value of maximum increase by looking at the magnitude of that. 9 plus 1, which is square root of 10. So this is saying if I'm standing at the point 1, 0 on this function, this is giving me the direction of the maximum slope, and that's the actual slope itself. Now that is not what this question is looking for. That's just kind of free stuff right there. Just kind of a review of what the gradient does for us. But it also allows us to find the slope in any direction. So let's see here. My rule says to take my gradient, which we found was 3, 1, and we're going to dot that with our direction vector. By dotting our gradient with our direction vector, it's going to give us the slope in our direction, in the direction of 7 pi over 6 from the point 1, 0. So let me see here. That's negative root 3 over 2, negative a half. That becomes negative 3 root 3 over 2 minus 1 half, and whatever that equals. 5 maybe, I don't know. But we're just going to leave that alone anyway. We don't simplify. But remember, this is simply put the rate of change in the z direction. Now let's talk about the difference. Remember, the gradient gives me the direction and the slope by looking at the magnitude. That gives me the direction and the slope of maximum increase. The directional derivative will find me the slope in any direction. So basically was, if I'm looking for the maximum increase, I look at the gradient. If I'm looking for the slope in a direction, I have to look at my directional derivative rule. So let's take a look at number 3 here. The first number 3, can't count. So it says to find the directional derivative if we're given our function here. Again, we're at the point x equals 1, y equals 0, and we want to move towards the origin. So of course the first thing I want to find is u, my directional vector. So that's not too hard to do. I'm starting at 1, 0, so we only are interested, remember, in the x and y coordinates minus the origin, 0, 0. This is my end. Remember, it's going to be the, see, I switched it around. Nobody told me that. There we go. Remember, sorry about that, I should have wrote this down. It's the end minus the start. Since we're talking about dels, we can sing a del. This is the end, my friend. So we're going to take 0, 0 minus 1, 0. Sorry about that. We're moving in the direction of 0, 0. And if we simplify this, we get negative 1, 0. Now this is a unit vector. So we're good. We don't have to convert anything. Next, we need to get del. So to get del, when we get here, this becomes y cubed minus 2x. Partial, remember, that's my partial with respect to x. That's right here. And now I need my partial with respect to y. 3x y squared, and this just becomes 0 right there. We don't worry about that. Find the gradient. Remember, at the point 1, 0. So this is saying, what this is going to tell me, at 1, 0, what's going to get me up the hill the steepest? Plugging in 1, 0, that just becomes negative 2, 0. So heading in this direction will get us up there the steepest. Remember, that's what this tells me. This is that gradient, right? This is that gradient. And it gives me the direction of maximum increase. Now, that's not what we're looking here right now. Remember, we want the direction heading in, we want the slope heading in the direction negative 1, 0. So we want Duffman. So my rule says take the dot product of del f, dot that with u. So we're going to go and do that. Del f we said was negative 2, 0. Dot that with u, which is negative 1, 0. And that's not too hard to do. We just get 2 right there. Pretty easy. Oh, here's a free question. Let me ask, let's see, we have room here? Yeah, we have some room here. What would be the direction of minimum increase? Well, our rule says that's just negative del. So that would be negative. That's we're looking negative there. It would be negative 1, 0, or 1, 0. It's the opposite direction. All right, that was for free. All right, so for number 3 here, let's take a look here. It's asking find del f given our function. So we're going to find that. That's not too hard to do. We can do this pretty quickly. Let's see here. The partials with respect to x, that's just 2xy squared minus 2x. Those become 0. That's my fx. Find the partial with respect to y. This becomes 2x squared y plus, be careful, 4y cubed minus 1. There's our partial with respect to y. Next it says find del f of 1, 0. Remember, this is really saying find the gradient. That's what this is kind of telling us right here. We want to find that gradient. So I'm going to plug in 1, 0 into my function up here. If I plug in term 1, 0, what's that going to give us? Let's see here. Let x be 1, y be 0. That's just going to become negative 2, 0, 0, negative 1. Right there. Now remember, this is our gradient. In other words, it's the direction of maximum increase. Okay? If I want to find the value of that maximum increase. Again, this is free today. In other words, I want to find the slope. I want to find the slope at that point, right? I want to find the slope of the gradient. Pretty much. So that is going to be our magnitude of del. That's what we're looking for. The value of the maximum increase is our del operator. So this is what the question was looking for. This is still an extra here. Take the magnitude, that's going to become 4 plus 1, negative 2 squared plus negative 1 squared, and we get root 5. So what this is the slope in the direction of greatest descent. That's what that's telling me. All right, the last example here. Write the directional derivative duff as a dot product of the function at 1, 0. So they're giving my starting point in the direction of the vector negative 5, 12. So right away, I should go and find u. So this is definitely not a unit vector. So I'm going to go negative 5 and 12 and divide that by, of course, its magnitude, right? So that becomes 25 plus 144, which is 169. That's just 13. So I can say u is therefore, what's that? Negative 5 over 13 and 12 over 13. Let me erase this. Come on. There we go. I think my pen's getting tired here. All right. Next, of course, we're going to need our gradient, or our del. Now, we're using the same function at 1, 0. We already know that that's negative 2, negative 1. So let's take a look here. We got u. We got our gradient, right? We have our gradient. So to get our directional derivative, we're just going to dot those together. So we take this negative 2, negative 1, dot that with negative 5 over 13, 12 over 13. And you can simplify that. That's 10 over 13 minus 12 over 13, or negative 2 over 13. And this is our slope. All right, another free one. What would be, so other questions I could ask. So what would be some other questions we could ask? Other questions I could ask now. What would be the direction of minimum increase? Right? That's easy enough to do. That's just the opposite of del. That would be negative del f, which would be negative, negative 2, negative 1. What would be the, excuse me, the value of the minimum increase? Well, that would be the opposite of the magnitude of del f, which I already have up here is 5, is root 5, so it would be negative root 5. So other questions we can ask on these, okay? All right, I hope you guys enjoyed this video. I will see you all later. Bye-bye.